Hello everyone. Today we are going to look at the first part of Chapter 7, Section 7.1, which is on Kepler's laws and planetary motion. Now the Edpuzzle video that you had for asynchronous work last time is also about Kepler's laws, and it's a nice introduction with no math involved. So if you haven't watched that Edpuzzle yet, I suggest you watch that first so that you have an idea of what I'm going to be talking about here. So our learning targets today are to be able to explain how Kepler's three laws apply to planetary motion and be able to use Kepler's third law as a formula to compare the orbit and period of two planets. And our essential questions we're going to answer today: how is planetary motion similar to and different from circular motion? What force keeps planets in orbit? And what is the relationship between a planet's orbit and its period? So here's our review. Let's think about circles for a minute. That's where we're starting from. So objects moving in circles have, what do they have that goes around the circle? Yes, they have velocity. Nicely done. The velocity goes around the circle. Objects moving in circles also have something that goes toward the center, which is acceleration. Good for you. Remember, they have acceleration because the direction is changing constantly toward the center of the circle. And finally, objects moving in circles have something else that goes toward the center. Yep, force. Good job. Okay, and the force is toward the center because it's pulling the object to stay in the circle, all right? Otherwise, the object would go flying off into space. Okay, so that's what we know about things in circles. So let's look at things going around the sun. So planets, great big things out in space. Planets moving in orbit have, yep, they also have velocity, right? Those planets move around the sun, and just like in a circle, their velocity is going around the orbit. Because the direction is changing, planets also have acceleration. And just like in a circle, that acceleration is toward the center of the orbit. And finally, if you have acceleration, you must have, yep, an unbalanced force. And that unbalanced force is also toward the center of the orbit. So planets moving in orbit act a lot like objects moving in a circle on the Earth. There is, however, one really important difference. And so let's take a look at this, okay? So if you compare my object that's moving in circular motion with my planet that's going around the sun, what do you notice? What you should notice, or what I hoped you noticed, is that this is a circle, but this, oh, that doesn't show up very well, does it? Let me try something else. This is not exactly a circle, right? That's what we call an ellipse. So this is a circle. This slightly flattened oval shape is called an ellipse. Okay? And by the way, as long as we're here, let's say what these forces are. The force that's holding this object in a circle is a pulling force, right? Because it's attached to a string. What's the force that holds a planet in orbit around the sun? Good for you. This is the force of gravity. Okay, that holds the planet in orbit around the sun. Okay, so Kepler. Kepler's first law has to do with planets in orbit and the shape of their orbit. So here we go. Kepler's first law. All planets orbit the sun in an ellipse. Okay, in an ellipse. Now I want you to look one more time carefully here. Notice that my circle has one point at the center, right? That is equally distant from every spot on the circle. My ellipse, however, doesn't. So my ellipse has two places in the center here, right? Not one spot, but two. And the distance from the spots is slightly different at different points in the circle. These things are called focus points, or if you want to talk about two of them, you can call them foci. Okay, so these are called focus points. And the sun is one of the focus points. And the other focus point is there isn't anything there, it's just space. Okay? So if we finish writing our Kepler's first law here, we're going to say all planets orbit the sun in an ellipse with the sun at one focus point. And there's nothing at the other focus point, it's just empty space, which is kind of weird, huh? Okay, so that's Kepler's first law. Take a minute, go back, make sure you know the similarities and differences between a circle and a planetary orbit. Right, they're different shapes, and the center of them is different. Okay, so let's go ahead and talk about the velocity of our planet. Now we know that the velocity is around the edge of the circle, but if you take a look here at this picture, each month has a slightly different length. Let's see if I can highlight that. So January is this long, but February is only that long, and March is only that long. By the time we get over here to July, it's only that long, and then it starts to get bigger again. But if I look at this whole space, I can see that one of those triangles, it's not quite a triangle, but similar, one of those triangles is kind of short and fat, and the other one is kind of long and skinny. And if you were to figure out the area of those triangles, they would be equal. So this triangle and this triangle have equal areas. And that is true of all the triangles. All the triangles in this orbit are equal in area. So that means that my planet has to travel further along its orbital path here than it does here, because on this side it's closer to the sun, and on this side it's further away from the sun. All right, so the area is equal, but the distance it's traveling around the perimeter is not. What's the practical application of that? The practical application of that is that when the planet is over here closer to the sun, it moves faster. Right? It's got to cover all this distance. In the same time, over here, it covers only this much. So over here, it moves slower when it's further away from the sun. All right? So Kepler's second law has to do with velocity. And so here we're going to say the velocity of a planet moving in orbit varies, or if you don't like varies, you can say changes, due to the elliptical shape of its orbit. All right, so it moves faster when it's closer to the sun and slower when it's further away from the sun. The way that Kepler said it was like this. Planets sweep out equal areas in equal time periods. And like we said, the practical application of that is that planets move faster when they are closer to the sun. Okay, so right now, underneath your feet, the Earth is moving faster because it's February than it would be in August when it's further away from the sun. You can tell that, right? Can't you tell the Earth is going faster right now? Yeah, of course you can. Of course you can. Okay, so Kepler's second law has to do with the speed the planet travels, right? How its velocity changes over the course of its orbit. All right, last one. This is the one where the math is going to get involved. So we're going to use this third law of Kepler's to compare the orbit of two different planets. All right, so in order to do this, you have to know information about two different planets. And these two planets look like they are maybe the Earth and Saturn with those rings. Okay? And so if we take a look at these two orbits, one of the things that you should notice is that Saturn out here is further away from the sun. It has a bigger orbit, right? It's actually a bigger oval than what the Earth has. And so if we're comparing the differences there, we should see that different planets have different sized orbits. And that's just because some planets are closer to the sun and some are further away. But it does affect their motion. So if I were to ask you which of these two planets is going to take longer to go around the sun, what would you say? Do you think Saturn is going to take longer to go around the sun, or do you think the Earth is going to take longer to go around the sun? Yeah, just by looking at it, right? You can tell me. It's going to take Saturn longer to go around the sun, right? It has further to go, so it's going to take it longer. So that's what Kepler's third law does. Kepler's third law compares the orbit and the time it takes the planet to go around the sun. So we're going to say planets with larger orbits take longer to go around the sun. Oh, I lost my line, didn't I? Okay? Planets with larger orbits take longer to go around the sun. Again, that's pretty logical. So then Kepler got all of his data that he had been collecting, and he figured out that there's a relationship between there that you can write as a formula. And the way that he wrote it as a formula is he took the period, right, the time it takes to go around the sun. We have planet A and we have planet B here. And he said, okay, well, if I take those, the ratio of those, and square it, then it's equal to the ratio of their distances from the sun cubed. Now, I just wrote that for you in like, I don't know, 15 seconds or something? It took him years to figure this out, right? He didn't just look at all those numbers and go, oh, that's what it is. No. It took him years to figure that out. Okay, but we're going to use this formula as if we just have always known it. So let's go ahead and make sure that we remember what all of our variables stand for. We know that R stands for radius. And in this particular case, because we don't actually have a circle that we're working with, in this particular case, we're going to call this the average distance. So that means the average distance. We take the short distance and we take the longer distance and we add them, short plus long, and then we divide by 2 and we get the average distance. Okay, so that's the number that we're going to use, the average distance. Okay, so radius is the average distance, and then capital T, of course, stands for period. And remember that the period is the time to go around once. So how long does it take the Earth to go around the sun? It takes 1 year. Or you could say it takes 365 days, right? Those are both a period. How long does it take to go around once? So RA is going to be the average distance from planet A to the sun. RB is the average distance from planet B to the sun. TA is the time for planet A to go around the sun. And TB is the time for, you guessed it, planet B to go around the sun. I just spelled the word around wrong. Okay. All right. So when you see this formula, you should know what all those variables stand for. Okay. Let's see. What are we going to use for measuring? So things in space are really a long way apart, and so instead of using meters or kilometers, we're going to use AU. An AU is an astronomical unit. Okay, and you can just think of that as a measurement of length. Like meters or kilometers, we're going to use astronomical units. And for period, we're going to use years or days as our period. We could use minutes or seconds, but that's a lot. Those are big, big numbers. So we're going to use years or days here. Okay? So, example problem. Here we go. Venus has a period of 225 Earth days. Earth, of course, is 365 days. The Earth is 1 AU from the Sun. How far is Venus from the Sun? So let's see what we know and what we're trying to find. So the problem tells me that the period of Venus, now instead of using A, I used V to stand for Venus, because that's going to help me keep it straight in my head. So the period of Venus is 225 days, and the period of Earth, and instead of B, I used an E because I wanted it to be the Earth, is 365 days. So far, so good. The the distance from Earth to the Sun is 1 AU. Again, I used RE to stand for the Earth. And what I'm looking for here is how far it is from Venus to the Sun, so RV. So here's my formula. Instead of A's and B's, I'm going to use R's and E's. I'm going to use V's and E's. So I've got TV over TE squared, RV over RE cubed. Okay, so instead of A and B, I used R and V. I used V and E. And then down here, I'm going to plug in my numbers. So I've got 225 squared over 365 squared. And over here, I've got RV cubed over RE is 1 cubed. All right, so stop for a minute if you need to. Make sure you know where all those numbers came from. Okay. So I am going to work up here since I ran out of space. So I'm going to plug this in my calculator. Now this is going to be much easier if you have like a scientific or a graphing calculator. So if you have got it in the bottom of your bag somewhere, go get it. That's going to make this much easier. So if I square 225, I've got 50,625. And if I square 365, I've got 133,225. And this is equal to RV cubed over, and 1 cubed is 1 times 1 times 1, so that's just 1. All right, and so now I'm going to divide. So if I divide these two numbers, I'm going to get 0.38. RV divided by 1 is RV, so RV cubed here. And now I need to take the cube root. So if you've never done the cube root of something before, you're going to push the math, M-A-T-H, math button on your calculator. You're going to scroll down to where you see a cube root, which looks like this, a little square root sign with a 3. You're going to hit that button and you're going to put 0.38 in there, push enter, and you're going to discover that the cube root of 0.38 is 0.72, and that's equal to RV. What would I label that? I would label that AU for astronomical units. Okay, so what that tells me is that Venus is closer to the Sun than Earth is, which is what I expected because it goes around the Earth faster, right? It only takes 225 days for Venus. It takes 365 days for the Earth. We will work on some problems like this in class, so if you got stuck in the math, don't worry about it too much. We're going to practice some more. But like I said, this is much easier if you have a scientific or a graphing calculator, so go find it if you haven't been using it. All right? If you have questions, we can talk about this next time in class.
and I will see you soon. Thank you so much.